All right, we are at section 19.2, specific heat and calorimetry. So let's share the PowerPoint, and we're showing here a glass of water and a little nugget of copper. So when energy is added to a system, no change in kinetic energy, and there is no change in kinetic energy or potential energy, the temperature usually rises. The exceptions may be uh, during the latent, during phase changes. You can put energy in and to melt ice, and it's still the water temperature is still going to be 0 degrees C. Um, so uh, when you put energy in and there's no change in kinetic or potential energy, then you normally get a temperature change. Um, so for example, the quantity of energy required to raise 1 kilogram of water uh, by 1 degree C is 4,186 joules. By contrast, the energy needed to raise 1 kilogram of copper is 387 joules. Um, the And we call this heat capacity. Heat capacity is C. Uh, Heat capacity, capital C, is the amount of energy needed to raise the temperature uh, of the sample by 1 degree C. Um, so water has a high heat capacity, copper a much lower heat capacity. Now, specific heat is the heat capacity per unit mass. So the specific heat is the amount of energy it takes to raise a particular mass by some temperature. So Q, if we just take everything, if we solve for Q, take everything the other side Q equals the mass of the item times its specific heat times the delta T. That's the amount of energy that you put in. And here's um, some specific heats um, in the table here. Aluminum 900, beryllium 1,830, cadmium 230, copper, and so on. You can see lead is very low, 128. Um, uh, and then we have other solids, brass, marble, ice is 2090, 2090. Liquids, water is 4,186. So it's the highest specific heat on this table. What would be the lowest? It looks like the lowest is mercury. No, even lead even beats it. 128, gold 129, mercury 140. Um, so as an example, if you have a half a kilogram of water uh, and 4,186 joules uh, times 3 degrees, you're going to get 6.28 times 10 to the 3 joules of energy to raise a half a kilogram of water 3 degrees. Okay, when the temperature increases, Q and delta T are positive. Energy is transferred into the system. When the temperature decreases, um, the Q and delta T are negative, and the energy transfers out of the system. Um, so let's, as an example, a potato in the microwave, the change in internal energy comes from the transfer of electromagnetic radiation equals MCT, the mass of the potato times the specific heat of the potato, not listed here, times the delta T. And a bicycle pump is the change in internal energy. You're doing work. If it's a manual pump, you're doing work to pump up the bicycle. That's also M, the mass times C times delta T. The and you'll feel that if you've ever pumped your tire, you hold the cylinder, you can feel the heat of the cylinder. You've been doing work and putting energy into the system. So specific heat varies with temperature. The temperature intervals are not too great. Then you can ignore the temperature variation and treat C as a constant. Um, the Let me see. I have a note here. So um, So when work is done on the pump, by identifying MC delta T as the change in internal energy, we have a better understanding of temperature. The temperature is related to the energy of the molecules of a system. Okay, let's do a little quiz. Imagine you have 1 kilogram each of iron, glass, and water, and all three samples are at 10 degrees C. Rank the samples from highest to lowest temperature after 100 joules of energy is added to each temperature. Well, let's go back and um, uh, look at the table. Oops, let's see. Oh, I just gave it away. If you look at the table, iron is 448. Now I forgot. Oops, I gave it away again. Iron, glass, and water. So iron is 448. Glass is 837, a little bit higher, and water, of course, is 4186. So if you rank this from highest to lowest temperature, after you add 1,000 joules of energy, the iron will be the hottest, then the glass, then the water. Sure enough, iron, glass, and water. Now, imagine you have 1 kilogram each of iron, glass, and water, and all three samples are at 10 degrees. Rank the samples from greatest to least amount of energy transferred by heat if each sample increases uh, by uh, by 20 degrees. And if you rank the samples from greatest to least amount of energy, well, the answer is water, glass, and iron. So we have a kilogram of each. Rank the samples from greatest to least amount of energy transferred by heat. Uh, you have to put the greatest amount of energy into the water to raise it 20 degrees. You less if it's glass, and the least if it's iron. Um, okay, the specific. Oops. Oh, it's doing that thing where it skips an image, and it's just an image of a seaside. I apologize for that. I don't know. Let's try to go back. It's just showing you like uh, an ocean. An ocean sea mountains on one side and water on the other side. And water with its highest, the specific heat of water. Water has the highest specific heat of common materials. So it moderates climates very well. My son used to live in L.A. and his temperature variations were always much less than we have, because the prevailing winds carry the uh, moisture over over uh, into LA there. Whereas in the East Coast, the prevailing winds tend to go out to sea, so you don't get the influx of of air. We can see that we get a lot of Gulf moisture, like even right now we're getting Gulf moisture, and so I think we had a high of 83 degrees. So moisture is moderates the climate. Um, so let's talk about. Sorry we didn't get that picture. It's a pretty picture, but it's all right. It'll show up on the PDF when I post it. Calorimetry. Now, calorimetry, we learned that the um, Q cold equals minus Q hot. So the amount that the hot, when you combine, um, like we did the experiment with aluminum shot or copper shot, we heated it up and we put it into cold water. The amount of heat lost by the hot shot equals the amount of heat gained by the cold. Now, you notice it has an isolated system boundary. That's why we used a calorimeter cup that was insulated. I mean, it had like a little air gap with a rubber ring that kind of isolated it from the environment, and the lid had a styrofoam on the top. So as best we could, we made it an isolated system. And so you put the hot shot into the cold water. Now it has to be cold water, because if it has ice, then you're going to transfer energy to the latent for the latent heat of ice. So as you you have the mass of the water times the specific heat of water and its temperature difference minus that's the Q cold, and the Q hot is the minus M of the material, mass of the material, let's say copper, a specific heat of the copper times the final temperature minus the starting temperature of the material. So we equate those in the mass of the water times the specific heat of water times the temperature difference equals the negative of the mass of the material times specific heat of the material times the temperature difference. So it's a transfer of energy from the hot to the cold. And we're going to stop there, and we're going to talk about latent heat in the next section.